this. Okay, today we are going to learn about optimization. And this is an important subject. So my lecture today will go together with the exercises this afternoon. And please do that, because this is how you learn it. Optimization. And I'm going to do it by first showing results for an elliptic and a hyperbolic paraboloid. Because this is one thing that can be used in order to characterize optimal points for a function of two variables. And then I will look at local extrema. And here I will use the Hessian matrix method. And then I will talk about global minimum and maximum on a compact set. A compact set is a set that is closed and bounded. So, let's see that. We start out by looking at these two quadratic surfaces. And I do it from this quadratic polynomial. We have a x minus c1 squared plus b times y minus c2 squared plus k. And we want to see how that looks in a spatial coordinate system. So first we assume A is greater than 0 and B is also positive. A and B is positive. So let's try to depict this. Function here. You can see that when this is positive, then these first two terms here are positive. Or they could be 0, and they're only 0 when x is equal to c1 and y is equal to c2. Then these are 0, and then you have that the functional value for this polynomial is k. So you can see that if you have, let me just draw the point, you have c1 here, and then you have, say, c2 here, and then you have your value, say, something like this. This is your k value. So you can see that whatever graph or graphical surface that this quadratic polynomial it will yield, it will lie above this plane here, the plane set equal to k. So it will be above that point, and this is a point on the surface. Now I could start out by drawing some contours of this this function here, And that is if I put this here, this function here, equal to a constant. So I could write it here. X and y equal to some constant I could call it k1. So if k1 is less than k, then there is no solution to that equation. But if k is greater than k1, then you can solve it and you get a x minus c1 squared plus b x minus c2 squared equal to k1 minus k, which is then a positive constant. And can anyone tell me what is this? What does this represent? A and B are positive. Have a clue? Yeah?
Parabola?
No, it's not a parabola. You see, they're both positive. So if you divide by the square of this, then you get the standard form for an ellipse. So this is an ellipse, and it is centered here. So if you draw the contours, you have this point, there's a contour, and then you can draw the ellipses. They have semi-axis here. So these are the contours of this function. Now, there is something about parabolas, so let's see that. And that is if we, now I want to draw a curve on my surface that is the section between this line here, x equal to c, or this plane here, x equal to c1, that is this vertical plane here. And how does that intersect with my function? If I put x equal to c1 in my expression here for p, I get this vanished, it's c1 minus c1. So I end up by having b times y minus c2 squared plus k. And this is a parabola. It is, and let me see if I can draw this. Like a line like this, and then since b is positive, the parabola is upturned, and it looks something like this. So imagine it is in this vertical plane. Well, similarly, we could put y equal to c2. Then we have px, and then this term here vanishes, and you end up with a times x minus c1 squared plus k. And again, you have a parabola, so it will be in this direction here. Let's see if I can draw this. That was not. So I'll show you a Mabel video later, so the drawings will be better. But you see here, whenever you cut this surface here with a vertical plane, you get a parabola. And whenever you cut it by a horizontal plane, you get an ellipse. And this is why this is called an elliptic paraboloid. And what we have learned now is that there are no values of this function below the plane z equal to k. There's only the single point k. So this single point here is a minimum of the surface. So I just write what the result is. It's an elliptic paraboloid, and it's upturned. And P has a proper local minimum. In C1 comma C2. What we're going to do more generally, then we'll make this quadratic polynomial approximation to the general surface, and then if this approximating polynomial is parabolic paraboloid of this type, then there is a proper minimum for the function as well. Now we assume that A is less than 0 and B is less than 0. Again, we can draw the function. We have the point here, and since these are negative now, then the parabolas will be downturned, and we have, if I draw the parabolas, they will look something like this, and again something like this. So here you can see that you will have, say, a maximum in the point. So it is a down-turned elliptic paraboloid, and P has a proper local maximum. Now, the final thing I will show you is that assume now that A is greater than 0 and B is less than 0. How would that be? X, Y, set here. So we have our point here, where I should write here, this is C1, this is C2, and this is K. So this is a value on my surface, and but what happens now if I take these restrictions? I put x equal to C1. Then I again get b times y minus c2 squared plus a. But now b is negative, and I will then have a parabola that goes like this. If I take the other direction, x comma c2, then I get a x minus c1 squared plus a. And a is positive, so this will go like this. And this is as far as I can draw this one. So I will, but the thing is here that this is upturned and this is downturned. So this will have, say, a saddle point in the point. So there's neither a maximum nor a minimum. And this you can in fact see, because if you go in this direction, you will have values below the level set equals to k, but if you go in that direction, in the x direction, you have values above k, so that cannot be a minimum or a maximum.
Sorry, I don't get why the positive is downturned.
Sorry?
I don't get why the positive is downturned.
B is negative. Ah. Yeah, you're right. So, my drawing is correct. But these were wrong. Sorry. Let me see if I can get this to work. So, I think I'll just make it a bit bigger. Okay, so here you see I have this polynomial with center at C1 and C2, and then I choose constants. And I would like to show you the elliptic one first. So you can see, if you look from above, you see the ellipses, and if you look from either side, you can see the parabolas. But you can see there is a definite minimum in the point. Now, let's try to see if I can have this function. Now there's different signs in A and B, so you have a saddle point. You see
if you have this point, and if you look at it in the x direction, you have this parabola pointing upwards, that is upturned, and then if you look at it from, or in the y direction, you have this downward pointing parabola. So this is a hyperbolic paraboloid. Okay, enough of this. So now we're going to use this in order to approximate general quadratic equations.
And what I'm going to do first is that I have a function f, and it goes from r squared into r. And then I take the approximating polynomial of second degree to that surface. And remember, first we should have, and I do it in the point x0, y0. So you have first the functional value, and then you have the linear terms, that is the x derivative of the function, and then the y derivative of the function. And then you have the quadratic terms. You have 1/2, and then the double derivative with respect to x in the point. And then this quadratic term, and also in the y direction, 1/2. And then in this point. And then finally the mixed term. Like this. So this is the general second degree approximating polynomial to the function f. Now I want to put this in matrix form. We have e plus x y is equal, we have the functional value here. And then you can consider this as the scalar product between the gradient of f and the point, because the gradient here is df dx, comma df dy, but it's x derivative, comma the y derivative, and then you will multiply it by this vector here, y minus y0. So what is standing here is the same thing as the linear term here. Similarly, I can use the Hessian matrix in order to write this second order term here. So here I multiply by x minus x0, y minus y0. And then I use the Hessian matrix. I shall write what the Hessian matrix is in a while. But this matrix here I use, and then I have to multiply by this as well. So this is the second degree approximating polynomial in matrix form. So let me just write you the Hessian matrix. So Hessian matrix is the second order derivatives. And then it is, let me get this right, xy, and then x0, y0, and then yx, x0, and y0, and then finally so this is the matrix that that is represented here, and if you perform this multiplication, multiply it by 1/2, then you will get these three terms. And you can see we only have f double prime xy here, that is this one. But remember, these two are equal. And this means also that the Hessian matrix is symmetric. And this is something that we are going to look at. What you can see now is that if the gradient of the function is horizontal, that is, if the derivative in the x direction is 0 and the derivative in the y direction is 0, then you have a possibility of a maximum or minimum. Because this means that the tangent plane to the graph of the surface is horizontal. And this is in fact a necessary condition for local extrema. They can only be found in the stationary points. And that is where the gradient in x0, 0 is equal to 0, 0. So this is a necessary condition for an extrema or an extremum in the point. So whenever you're going to look at for extremas, then find the stationary points. It's a good thing. So now we're going to look at the special case where we are at a stationary point, and that is when the gradient of the function is 0. So if we have that the gradient of f is, then our approximating polynomial looks like this. X minus x0, y minus y0. And then you have the Hessian matrix, and you have x minus x0, y minus y0. But also you have this value here. This vanishes, but you have this value that we call this for k. Then you have also the value k. But since the Hessian matrix is symmetric, it's possible to find an orthogonal matrix, so you can make a change of the coordinates so that so to get rid of these mixed terms here, because you see, if you are in a special case where there are no mixed terms, the Hessian matrix here becomes a diagonal matrix, and then you can see that it's actually the sign of these double derivatives, x and the sign of y, that determines whether you have a maximum or minimum, or you have neither. And if you have a diagonal matrix, then the elements in the diagonal are the eigenvalues of that matrix. So, but the thing here is that we should find a positive orthogonal matrix Q and a diagonal matrix lambda, which are where these are the eigenvalues of the Hessian matrix, and then we can write this lambda matrix here as the orthogonal matrix times Q, and then we can make our change of coordinates. And like we did the last time, we introduce x, y as this orthogonal matrix times new coordinates. But remember now, we do not have x, y, we have x minus x0 and y minus y0. So what happens to the point x0, y0? Remember, an orthogonal transformation is a rotation of the coordinate system. So let's say that this is the direction of, I should write down what Q is. Q is simply the normalized orthogonal eigenvectors for the Hessian matrix, and these are orthogonal and they have unit length. So if this is Q1, you can draw Q2 here. And let's say that this is our point C1, C2, or no, sorry, not this one. It's x0, y0. So this is say, our development point, and we want to find out what is, how does the function vary in a point x, y. But then we need to find the new coordinates, C1 here, and C2 here, in the new coordinate system. And if we do this, then we get one half, and then we get x1 minus c1, y1 minus c2. These are the new variables, and when we do that, we can replace this by the diagonal matrix, and then we multiply by x1 minus c1, y1 minus c2, and then we have, in addition, this constant here. Now, if you multiply this out, you get 1/2 lambda 1 x1 minus c1 squared plus 1/2 lambda 2, and then y1 minus c2 plus k. So, in fact, you have depending on the sign of these eigenvalues here, you have either an elliptic paraboloid, or you have a hyperbolic paraboloid, or you have neither. But if they both are different from 0, you have one of these types. So you can characterize that stationary point. I just need a bit of space here. So now we assume that lambda 1 and lambda 2 are greater than 0. And what we see then is that then from our previous analysis, we can see that P2 is an upturned elliptic paraboloid. And then we know that P2 has a proper minimum in the point, but since it is an approximation to our curve, then F has a proper local minimum. In x0 and y0. Maybe I can make a sketch of this. have x, y, z. And here you have this parabolic upward or this elliptic paraboloid that is upturned. And this, in a sense, is then the approximation of a more general surface, like this. But since the difference between these two are really small, then you can say that f has also a minimum at that point. And let me just take two other cases. We assume that lambda 1 is less than 0 and lambda 2 is less than 0. Then P2 is a downturn elliptic paraboloid and f has a proper maximum at the point. In the stationary point, x0 from x0. And finally, we assume that lambda 1 has different signs, that is, the product of the two is less than 0. Then P2 is high parabolic paraboloid. And F is a saddle point. And there is there's no extremum. Yeah.
So there is C1 and C2.
That what?
What is C1 and C2 up there?
C1 and C2, these are the coordinates of the stationary points in the new coordinate system. I draw it on the figure.
What about X1 and Y1?
You see here, if you have x in this form here, you have x minus x0. And y minus y, y0. And then you want to transform this into new coordinates. So you get that x, y is equal to q times x1, y1. And you get that x0, y0 is equal to q times c1, c2. And this is what I have shown here. Here you have these new coordinates for x0 and y0. Okay, I'll take a break now, and we start again at 11 o'clock.